In this video, we're going to be talking about some examples for pressure-volume loops. Now, before we begin, there are a couple of rules that we should consider and thoughts we should consider. The first is that you should try to look at only the primary change first. Next, we should start thinking after we make that change, how will the other variables be affected for a compensatory change? And finally, a third principle, which I think is extremely important, is that the secondary changes that we see after making a primary change will attempt to undo the primary changes, and partially do, but they never will completely undo the primary changes. Let's begin by looking at determinants of ventricular function. These will include preload, afterload, and inotropy. Now let's go ahead and take a look at our pressure-volume loop. We've inserted it in here over here. And let's remind ourselves of what we use to estimate each of these values. For preload, we typically use end diastolic volume, which again is an estimate of preload. Afterload, we use ventricular wall stress, which is related to pressure of the ventricle times the radius of the ventricle divided by the thickness of the ventricle. And inotropy is typically estimated with ejection fraction, which we will remind ourselves is the stroke volume over end diastolic volume. So let's consider a case where we give fluid to a patient, and that would be described as increasing the patient's intravascular volume. So the primary change that we're going to be looking at here is an increase in the patient's preload. Now remember above, end diastolic volume is our estimate for preload. So if we were to begin drawing our first change, we see a shift in the right in end diastolic volume. That will be shown with these blue dots. Now contraction will begin at this higher end diastolic volume, and we'll note that the pressure within the chamber during isovolumetric contraction does not need to rise above the value that it did before in order to begin ejection into the aorta, and that is because afterload right now has not changed. So we'll go ahead and observe the ejection period of the cycle, and we'll see that we return to our original end systolic volume. Now notice that we have an increase in stroke volume with this primary change, and let's remind ourselves that cardiac output is defined as heart rate times stroke volume, and that blood pressure is defined as cardiac output times peripheral vascular resistance. So when we have caused an increase in stroke volume, we cause an increase in cardiac output, which an increase in cardiac output corresponds to an increase in blood pressure. An increase in blood pressure will be an increase in afterload because we require an increase in intraventricular pressure to provide a wall stress that can overcome this pressure. Additionally, we can see that an increase in end diastolic volume leads to an increase in the radius of our chamber, and that will lead to an additional increase in ventricular wall stress. So we can therefore see that our secondary change is an increase in afterload, and that will be reflected on our pressure volume loop. We will begin by drawing our diastolic filling phase in first, and when we reach isovolumetric contraction, we'll note now that we need to be at a higher pressure before we can begin ejection from our ventricle into our aorta. So we will observe that that will occur, and because of the higher afterload on our ventricle, we can't squeeze out as much fluid as before. Therefore, our stroke volume will see a decrease, and bringing down our isovolumetric relaxation line, we will see that this ultimately corresponds to a right shift of end systolic volume. So let's go ahead and summarize what we have here. First, we'll remind ourselves of our stroke volume equation, which is stroke volume is equal to end diastolic volume minus end systolic volume. And we'll look at our primary change, which was to largely increase the end diastolic volume, and that produced a large increase in stroke volume. Our secondary change, which was to increase our afterload, ultimately caused an increase in end systolic volume, which actually leads to a decrease in the stroke volume. However, in net, what we'll see is that the large end diastolic volume increase that we saw from increasing preload as our primary change against our increase in end systolic volume from our secondary change ends up producing a net increase in stroke volume. So once again, the primary change ends up beating the secondary change and resulting in an overall increase in stroke volume. Let's now look at a case where we give a medication that decreases arterial blood pressure. For example, we could give hydralazine, and let's take a look to see what these effects would be. So Our primary change would be that we would see a decrease in afterload. And again, this is because we've decreased arterial blood pressure, therefore we decrease the ventricular pressure that we need to generate to push blood from the left ventricle into the aorta, and therefore we do not need to have as high of a ventricular wall stress. This all makes sense as the ventricular wall stress is a measurement, effectively, or an estimate of the afterload. This will mean that with a decrease in afterload, we're able to generate a greater ability to push blood out, so therefore an increase in stroke volume. And we'll go ahead and plot this. So our diastolic filling remains the same, and now because we have a decrease in afterload, we don't need to push as hard in our ventricle during isovolumetric contraction for blood to be ejected out. So blood gets ejected out. This now is being shown as a increase in stroke volume, and we bring down our curve in isovolumetric relaxation, and we'll note here that end systolic volume, as we might expect, pushes to the left. So what might be the secondary change? Well, we decrease the end systolic volume, as mentioned, and when we add in venous filling to this decreased end systolic volume, we end up getting a decrease in end diastolic volume. So that ultimately means if we look above at our determinants of ventricular function, we will get a decrease in preload. So let's go ahead and see what these effects are. Starting back on diastole, we'll draw a dotted line here, but remember our end diastolic volume has shifted to the left, which I've marked out here in blue, and then we will see ventricular contraction at this point, and at the appropriate pressure that we need to open our aortic valve, we will then see a similar following on the rest of our pressure volume loop. So reviewing what this overall means are, again, stroke volume is end diastolic volume minus end systolic volume, and our primary change was to increase stroke volume and thereby decrease the end systolic volume. Now that will lead to, again, an increase in stroke volume. Our secondary change was to provide decrease in end diastolic volume, and that gives a compensatory decrease in stroke volume. So overall net, we will see a decrease in end systolic volume, a smaller decrease in end diastolic volume, and net an increase in stroke volume. Now, just to note over here, when we're subtracting negative arrows, as in subtracting end systolic volume, which I've drawn 2 down arrows for, that corresponds to 2 up arrows for stroke volume. This last example is a little bit trickier, so bear with me on this one. We're going to consider the effects of administering a beta blocker. We'll recall that the effects of a beta blocker, such as metoprolol, will be to decrease inotropy. So our primary change in this situation is a decrease in inotropy. What we're going to see is that is going to decrease stroke volume, and we'll also see that we'll see a increase in end systolic volume as our primary change. So we'll start out with diastolic filling, which goes as before, and with isovolumetric contraction at the end diastolic volume from before. Then with contraction, we'll see that we don't contract as much as before, and therefore we don't eject as much as before, so our stroke volume has decreased, and we'll therefore see that we will have an increase in end systolic volume. Now we should also draw in our new end systolic pressure volume relationship, as inotropy has decreased, which brings down the slope of this relationship. Again, this is our end systolic pressure volume relationship. What we're going to see now are the secondary changes. So we've increased end systolic volume. Recall that when we add this to venous filling, we will see a increase in end diastolic volume. Looking at our determinants of ventricular function above, this means we will have an increase in preload. However, we'll also note that there's a second change, and that is because there's a decrease in stroke volume, which we remember from before means a decrease in cardiac output, which also means a decrease in blood pressure, and ultimately means a decrease in afterload. So these two effects are our secondary change. Now we'll go ahead and start by drawing in our diastolic filling, and as we mentioned before, we have an increase in preload, therefore an increase in end diastolic volume, so we show that with a rightward shift of our end diastolic volume. Now, we also had a decrease in afterload, so during isovolumetric contraction, we don't increase to as high of a pressure as before for our ability to begin ejecting volume. We'll notice here that because of our change in our afterload, we have effectively increased our stroke volume, and we'll see that by now a leftward shift of our end systolic volume from our primary change. Now, the changes we have observed are a little bit difficult to wrap our minds around, so let's go ahead and walk through step by step. Let's first bring back our stroke volume equation. Now, what we're going to do is first talk about our primary change, which was to decrease stroke volume. I've used 3 arrows here because it will make the following steps a little bit easier to understand. So the decrease in stroke volume was accomplished by increasing the end systolic volume. We next saw as a secondary change an increase in preload as one of our effects, and also a decrease in end systolic volume as an additional secondary effect. This led to an increase in stroke volume, but not as high of an increase as we saw the decrease of the primary change. So overall net, we saw an increase in diastolic volume, a net increase in end systolic volume, and an overall net of a decrease in stroke volume. Now again, our primary effect was to decrease stroke volume. Our compensatory change is to increase stroke volume. Overall, though, the primary change wins, and we see a decrease in stroke volume when we administer a negative inotrope. This concludes our discussion of pressure volume loop examples.